Hello. In this episode, we'll discuss about what a long short-term memory neural network is. Okay. So this one is actually fairly popular in time series forecasting. It keeps tracks of the past, and in time series forecasting, using the past data is what we use to predict the future. And this happens to be a very popular neural network component in making time series forecasting. It's being used in, for example, in the speech, the natural language processing, but also oftentimes in just economic data time prediction. So let's see what this is. So the argument here is that in time series forecasting, we use past data to predict the future data. And oftentimes the past data often has an inertia, it has a momentum that carries over to the next period. So there's a past dependency. If the past GDP was high, then the next period GDP is likely to be high, and so forth. And that led people to consider an output feedback, meaning the past output, and incorporate it into the loop to implement. And in the usual time series analysis, we have AL1 process, the autoregressive process. And here in the neural network, people came up with a similar idea. We want to use the past output and feed it into an input, which is called a recursive neural network, which uses the X input and the current past output to feed it back into it. Okay, so that's what we do. And this technically by itself cannot be back propagated and trained away. So what people do is that they have an unfolded picture of it here. So for each time input, actually this is -2. Okay. So we have the xt -1 and the output from the t-2 period coming in to predict the ht-1, and then use that ht-1 and xt to predict the ht, and then use that ht and actual ht and xt+1 to predict the ht+1, and so forth. And that was the autoregressive idea, which is supposed to work very nice, but there was one problem, which is that when we do the back propagation, the gradient which we guide how the weight should be adjusted, that in the near the very last output layer, in the very last time period, the error gradients are fine, but it keeps shrinking and shrinking and shrinking, for example, or the opposite of exploding. So we do have that problem, and then people thought about an adjustment to this, and that's why the long short-term memory by Hochreiter and Schmidhuber 97 came out to be. It basically carries an additional internal cell state to keep track of the long-term memory, meaning you have the xt and then you want to spit out the ht here, so from input to output, based on the past output, but also some internal state called cell state. We'll discuss what it is more detail, but it keeps track of the long-term memory and try to mitigate the vanishing gradients problem. Okay? So it's just like this unfolding. It's being shown a picture of unfolding. So use the past cell state and the past output and input to predict this, and then use that and updated cell state and input to predict this, and so forth, isn't it? So how does this inside of the long short-term memory gate look like? Well, we'll go step by step, but it basically have some component like input and output. And also it does receive what we call a cell state from the past and the previous output as an input along with the input to predict the output. And then of course we pass to the next period, the updated internal state, the cell state, and that output to the next. Okay. And inside here, we have some what we call sigma. This is the sigmoid or the logistic output function, which looks like this. Given what comes in here, it squeezes the shrinks that input into between 0 and 1. In this long short-term memory, we could consider this as a switch. So if the input value is very small, it's 0. So whatever comes out here, it's multiplied with the forget gate. So for example, so then it's kind of shuts down to 0. So it's a switch off, but it gradually switches on for a large value of input, isn't it? Also, there's a hyperbolic tangent here, which basically shrinks whatever input is coming in here between -1 and 1. So it kind of regulates whether there is a negative signal or positive signal, a very large signal or very small signal. It just basically cares about that. Okay? Broadly speaking, there's a forget gate, there's an input gate, and there's an output gate, and we'll explain what they all are. But this is sort of how a long short-term memory is composed, with forget gate, input gate, and output gate, and it takes a past cell state, an output, an input to predict the current output, and passes on to the next period, an updated internal state and an output. Okay. All right. So let's first look at the entry part here, which we call the forget gate. Here's the forget gate. Okay. And again, it looks like this switch. You can consider that sigma, the sigmoid activation function, as a switch. What it does is that, well, what does this do? Well, it takes the H and X, the past output and the current input, and in a neural network weighting, so let's call this neural network transformation, WF, the weight of these WX and H's plus a bias, and goes through this sigmoid activation function. So if there's aggregated H and X, the aggregated H and X weighted average comes out to be a very small number, then the sigma will shrink it down to 0. If it's a very large number, then we'll push it to 1. So it's a passes through a switch. So that's what we call the forget gate output at T. Okay? So that forget gate has a sigma activation, act as a fraction of previous long-term memory, the cell state. So here's the previous stage cell state. So it's a 0 and 1, between 0 and 1 kind of number. It's multiplied with the CT. So what it will do is that if this forget gate gives 1, then this long-term memory from the past state goes in there unmitigated. But if the sigma gives out a number close to 0, then CT plus 1 is basically shrunk down to 0. The switch is off. And that's why we call it's a forget gate. It acts like a switch. By multiplying this number between 0 and 1 into the previous cell memory, it decides whether to remember the cell state, like when it's 1, or forget it when the sigma is close to 0, isn't it? So this is the forget gate. It basically controls how much of the past memory, the long-term memory, we're gonna pass to the next period, okay? So this remembers only parts of the long-term memory and forget the rest. So that's what's happening here. Decide what to remember based on the current input and the working memory. So here's the working memory, and here's what's the output. Again, comes out as number between 0 and 1, and it decides how much of the CT minus 1 gets passed to the next stage. Okay, so having passed the forget gate, the middle part is the input gate. And what does it do? It remembers some parts of the current input, okay, and previous working memory. So here is what it passed through the gate. So here is the past output and the input, and it goes through this gate, okay? So again, the sigma is like a 0-1 switch, a gradual 0-1 switch. So if the HT minus 1 and XT going through a neural network aggregated is a small number, then sigma will give out a 0. And if it's a very large number, it will give out a number 1, isn't it? Okay, so that is what this input gate does. Also, this H and X goes through a hyperbolic tangent and gives what we call an input information. It gives a number between -1 and 1. If it's a very small number, then here's -1. If it's a very large number, H and X weighted by the neural network, then if it's a large number, then it gives a number 1. Okay, so here's a 0-1 switch, and here's a -1 to 1. Okay, And what's being multiplied here gets the what we call relevant input information, which is the input gate minus input information. So a number between 0 and 1, and here it's basically h and x. It will basically tell whether it was a very small number or very large number by telling -1 or 1 signal here. Multiplying this together will get you the degree of a number between -1 and 1 if it's a fully switch on, and if it's a very small number, it's 0, then it will be 0 anyway, isn't it? So meaning the sigma input gate has this sigma activation as the previous stage in the forget gate, and decides what fraction to consider from the h and x, the parameters h and x. And the input information has a tan h function, which squashes between -1 and 1 here. And resulting is what we have, this relevant input information could be ranging from -1 to 1 or smaller, like shrinking down to 0. So that's what the input gate does. And then we update the long-term memory. So given that we got a number between -1 and 1, and then we added onto the remembered cell state from the previous stage, which was filtered how much to forget and mitigate it or not. We add them together to update and have the current long-term memory, the remembered cell state plus the relevant input information, isn't it? Okay. And that's our updated CT, which will pass on to the next stage. And finally, so the H and X going through a switch again, squash down of between 0 and 1. It's on passing through an on-off switch. Having said that, we retrieve some working memory. So the CT is here, the long-term memory. Decide what to retrieve based on the current input and previous working memory. So the CT goes through a hyperbolic tangent to retrieve the memory. So if the CT is very large, then a number 1 will pass through. If it's a very small CT, then -1 will pass through. We multiply this between a 0-1 switch and then push it out as HT, the output. So output gate gets here, isn't it? So the output gate hit again here on sigma activation, which is deciding what fraction to keep among this H and X. And the retrieved memory has a tan H function, which shrinks it between -1 and 1. And the product of it will be passed on to the output gate here, as well as the output here, isn't it? All right. So this is what the long short-term memory does. It not only passes the H here, the output that we want to get, but also keeps internally passing from period to period of what we call a long-term memory, which is regulated how much to retain each period and how much to reflect in the current output. Okay. So this was a brief overview of the long short-term memory, which we can use for time series forecasting. Thank you for watching the video.